Now we continue with our domestic installation. Before we finish up with the intake points, there is one more device I want us to look at. Now, where a lot of exposed metal parts exist in an electrical installation, in electrical domestic installations, for example, we have got cookers, electric iron boxes, electric cookers, etc. The consumer units can be fitted with residual current devices. Now, this sometimes referred to as RCDs, so that the whole installation is protected against any unbalance between the currents flowing in the live and the neutral currents, which an earth leakage fault would produce. Remember, we said that the ECC and the neutral should be separate. So in case some current goes in through the live, the same current should go back through the neutral. So introduce the RCD device so that in case there is an imbalance, which means some current leaked somewhere in the installation, then the RCD device, earth leakage circuit breaker, it's also referred to as an earth leakage circuit breaker, would disconnect the circuit. And I think I'll do this one through an example. For example, you are asked to draw a wiring diagram of a consumer unit for a residential building. The unit should incorporate an earth leakage circuit breaker and the 4 final sub-circuits. Now, for our solution, first we need the schematic diagram. But specifically, this one was not asked for here, but let's go through the stages. We have the schematic diagram as we saw it the other time. We have got the cutout provided by the PLC, but they have an HB, high capacity breakage fuse. Then we have got the energy meter, and we said the energy meter, the cutout, they belong to the KPLC. And then we have got the main switch for the consumer. And then here we have the consumer control unit, or a panel, where now the residential building takes off the currents. So this one serves as a schematic diagram for the installation. Now we intend to do the wiring. I think we are familiar with the wiring from the cutout to the energy meter to the main switch. So the difference we ask will be in the consumer unit or consumer panel incorporating the earth leakage circuit breaker with the 4 final sub-circuits, which is what we are going to draw now. Now, as I was explaining on the table, we've got the cable sizes, and here we've got the rating factors. Now, for ambient temperature, there are two values of figures given. One is rating factor for cables having cause excess current protection. They are the figures I explained about. And then we have got another row here, rating factor for cables having close excess current protection. Now the definitions of those two, they are also given in the I regulations. Now here we have got the first definition of close excess current protection. Now this is whereby the protection, which will operate within 4 hours at 1.5 times the designated load current of the circuit which it protects. Now the 1.5 times will be brought about by the fuse or circuit breakers that you choose for your circuit. Now that will be close. The protective devices, they should operate within 4 hours if the excess current continues at 1.5 times. That will be by the devices you choose for your protection. Then we have got cause excess current protection. This is the protection which will not, in this case, will not operate within 4 hours at 1.5 times the designated load current of the circuit which it protects. So you can see there are different rating factors for each. For the close, I think is slightly lower figures than for the cause protection. And then down here, they have talked about the way the cables are. They have said they can be clipped direct, or they can be put in conduits or trunking. Now, before we start on that one, when you have your conduit or trunking, there is a limit of number of cables that you can put inside your conduit. If you have your conduit, something like that one, there's a limit of the number of cables you can put in. They have got another table for it, but I normally use, for my purposes, use the space factor. Somewhere in the column, the I regulations, somewhere in the I regulations, they do give what we call the space factor for conduits, ducts, or trunking. Now, the space factor is simply a ratio. The cross-section area of the cables, you divide it by the cross-section area of the conduit, give it as a percentage. Now, it means if you are using conduits, which in most of the domestic installations we use conduits, that should be 40%. We should not exceed 40%. In other words, the area, cross-sectional area, occupied by these cables here should not be more than 40% of the cross-sectional area of your conduit. The 35 is for ducts, and for the trunking is 45. And of course, there is a condition such that there should not be more than 2 90-degree bends in the runs. Remember, you have to pull in the cables. If they are more than 90, you can bend your insulation. Now, the cable, as we know it, when you talk of the cable, in this case, we have got the conductor, which is the material which will be carrying the electrons. So this is the metallic portion, the metal portion, the conductor, and then you have got insulation. Now, the insulation is what determines how much voltage the voltage can withstand before it leaks out. This one will be laid somewhere on a surface which may be aft. Now, the insulation will determine what voltage can appear here between this one and the earth before there is a leakage. So it's very vital we protect the insulation. It has got a bearing of the specifications of our cable. Then sheath may be added. Sometimes, as you can see from the table is mentioned, you can lay the cables on the surfaces. Since you have to protect the insulation, if you are putting your cable on the surfaces, then you have to provide the sheath so that it protects the insulation. And sometimes you may need to run a cable outside of your house, maybe to do some work outside there. Then you need an armored cable, again for more mechanical protection. So in this case here, in case you are putting it in conduits, then we calculate the area. Now, the area of each cable will be the area of actually you use the dimensions of your insulation. So if it is circular, you get your diameter, then we know the area will be pi d squared over 4. And then if there are so many of these ones, you multiply the number. If they are the same size, if they are different sizes, you add them together, and then you calculate the size of your conduit. That area of your cables inside should not exceed 40% of the conduits. Now, if you move back onto the table, again, they talk of number of circuits, pairs of cables, single phase or DC, 3 cables per circuit, where one of them is neutral, blah, blah, blah. So in this case, number of circuits. If in your conduit you have got if you have got 2 circuits, then you derate this current carrying capacity by 0.8. And if there are 5 circuits, you get a factor of 0.59 for your current carrying capacity. So you can see the current carrying capacity of our conductors is affected by so many other conditions. And that's why, for example, you are finding that a current carrying capacity of 11 amperes, we are using it to do lighting circuits. And our lighting circuits, they are carrying currents in the order of milliamperes. So these derating factors are the ones which lead to that kind of a scenario. So if we work out a small example here, before we move on to see how we apply these factors here, maybe you have got a lighting circuit or a circuit whereby it's operating at 40 degrees centigrade. And let's assume we have got close excess current protection. And then there are 3 circuits. maybe let's assume they're in a conduit, and you have got 3 circuits. Now you have to apply the derating factors to our cable. So if the cable you're using is the 11 ampere one, this is the 1 mm cable. That is the diameter of the strands, the one we talked about, 1 mm squared, the cross-sectional area of that cable there. So in this case here, at 40 degrees, we have to apply a rating factor of 0.87, then we multiply by the other factor. We have got 3 circuits at the bottom here, 0.69, and then we multiply by the 11 amperes. Now, if you are using that cable in that kind of a scenario, that will be the current that that cable can carry. If you work that one out, 0.9, 0.7, 0.63, that will come to about how much? So you can see when you apply, that's why I say the terms, instead of them being rating factors, they're actually the rating factors. So if the temperature is higher, and then we are having 3 circuits, then from the tables you apply those factors. So you can see when you're insulating this kind of an area, environment, you can see now that same cable, although it is rated 11 amperes, then when you are doing our design, we have to design it such that it can carry, our design such that the maximum current will go from it will be 6.6 amperes. So these are factors you need to take when you are doing design work for your installation. That means the way you wire installation in Nairobi should be slightly different than if you are doing it in Isiolo, where the temperatures are a bit higher. But in case you go to the North Pole, the current ratings will be on the higher side and not on the lower side. And then we said, now these ones, you install them. There are also other factors you need to include. Now when you are doing your installations, there are various ways you can do your installation. One of them is to clip your bits on the board. Now, when you are doing your installations, there are various ways you can do it. Now the first one is what they are calling surface wiring. Now, when you are doing your surface wiring, it means we need protection for our installations. So surface wiring, all the cables must be sheathed. So here in the first column, and then surface wiring, you need to support them. If they are climbing on the wall or ceiling, you need to do their support. So another table, table B2M, spacing support for cables in accessible positions. So in this case here, they have given the overall diameter of the cable, not exceeding 9 millimeters, 9 millimeters to that, 15, 20, like that one. And then they talk of horizontal. In case the cable is running horizontal, that will be the spacing of your support clips, depending on the size. And then in case it's running vertically, that will be the spacing of your supports. Of course, you can see that the vertical is, they can be spaced a bit more than in the horizontal positions. Here the gravity is more pronounced than in this other case here. And then in the other column is for armored cables and corrugated aluminum sheath cables, mineral insulated cable and sheath cables. So they give you the supports you need. So that is something you need to bear in mind when you are doing your installation. Now there is another table. Here, now they talk of minimum internal radius of bends in cables for fixed wiring. Well, surface wiring is also referred to as also the fixed wiring. And then we know once you are running your installations, sometimes you may need to bend your cable. If this is your cable, you are taking to a lighting point, you need to bend that cable. So this table, again, this is B1M. It gives you the minimum internal radius of bends in cables for fixed wiring. So here they talk about rubber or PVC cables, circular, stranded, or aluminum conductors, not exceeding 10 millimeters. That means the minimum radius should be factor to be applied overall diameter of the cable to determine the minimum internal radius. Now in this case here, this is the radius. In this case here, this is the radius of my bend. So I'm told in the first category of cable, not exceeding 10 millimeters, a factor of 3. So in this case here, if I'm using that cable there, 10 millimeters, I multiply by 3, which comes to 30, which means that radius there must not be less than 30, which will be 10. The R there should be 10 times 3, which is 30 mm. Now, a rough way of doing this one here is when you plot when you are doing your installations, there are the lines, the marker lines that you draw. You simply, in this case here, you mark 30 here, and the other 30 there, you draw a straight line there. So when you are running your cable this way, it means it should not lie on this area here. If this one here is 30, and this one here is 30, your cable, if it's running, it should not lie anywhere on the inside of the shaded portion, so that it's within the minimum radius of bend. When they give the minimum, if you bend the copper inside your cable, it can crack or other things can happen to it. That's why they give those figures there. So that's another table you need to go through. And it gives PVC, solid, minimum, blah, blah, all the information you need, overall diameter, conditions, and then the factor you need to multiply by. So basically, you need to have that kind of information before you start doing your actual installation. Other tables are also available in the IE regulations, and it's good you familiarize yourselves with them. Come on, Jack. Lighting. So now we have learned briefly about the consumer control unit, something little about the cables, so we can start off with the circuits that are found in our domestic installation. So the first one I'm going to start with is the lighting final sub-circuits. Now, when we are doing design, maybe for a house, there are some things we need to take into account. Of course, the first one is the lighting points. The lighting points, this is where we shall connect our lighting. Now, the assumption is IE regulations lets us say, so we assume the power consumption will be 100 watts for every lighting point. So here you can see the current involved. If you apply the Ohm's law, I think it's I is equal to P over V. The power is 100 watts, and the voltage is 240 volts. Then this one works out to 0.416, which is approximately, this is amperes. We can talk about milliamperes. Itakuwa ngapi? 60. So you can see, if you work out the assumption we normally take for each lighting point, about 100 watts, it comes to about 420 milliamperes. Now you remember the current we talked about for the 11 ampere cable using for lighting. That one carry 11 amperes, and this one is 420 milliamperes. So that cable can supply a lot of currents, a lot of lamp lighting positions. Now in the market, the smallest circuit breaker we have is one of 6 amperes, MCB in the market. I think there used to be 5. I think the smallest now we have nowadays is 6 amperes. 6 amperes. C6. So you can see now this 1 MCB, if you work out the number of lamps it can protect, this will be 6. If I move back to the amperes, 6 amperes we divide by 0.4. That one comes to about 60 divided by 4, that to about 15 lamps. About 15 lamps. Somebody can ask, we have got 5 lamps, which comes to about 1.5 amps. How do we protect it with an MCB of 6 amperes? Now this is sometimes whereby the RCD device becomes handy in case you have got some problems. But in practice, we don't have the MCB controlling so many lamps for obvious designs. You can see if this one goes, all the 15 will go out. So when you are doing your design, you weigh some things. So maybe you can have one MCB controlling about maybe 5 or 7, and then the other one to control the balance. So those are things you need to have in mind when you are doing your design work. And of course, the other key thing we remember is the voltage drop in the cables. So you can work out the length, how far your lighting bit can be from the circuit. So I think we can work out an example on this one here. Briefly, I think those are the basics you need to know when you are doing your circuits. Now this one you can say the smallest cable. Capacity, 1 mm squared is about 11 amperes. If you add the rating, it may approximate maybe to about what you saw is about 6 amperes also, the rating factors. I think this ones we had done it earlier. Maybe 6 amperes. So the deteriorating factors, although the cable is 11, the deteriorating factors will take the current capacity down a bit lower. Maybe that's why the MCB is around 6 or something like that. And of course, the other thing, how far can this one be from the consumer unit to where the lighting is? Remember, drop in the cable, drop in cable is allowed to be 4%, which I still worked out to 9.6 volts. And we also know the incoming, according to IE, nominal voltage. It can vary by, drop is 4%, is plus or minus 6%. This is the 240. The nominal voltage in our case is 240 volts. So you can see in the worst case, when this voltage is in the negative and the distance in our cable is so much, then the loss will be 10%. So out of the 240, only 240 minus 10% of 240 is 24 volts. You are left with 216 volts. Yes, Abuni sawa. 216 volts. That is the worst scenario, the voltage you can play around with. the drop in the cable 4%, the nominal voltage, KPLC, it can go plus or minus 6%. If we took the minus, it will be 260, whereas on the higher side, again, it can allow us to go higher. This one will be 264 volts. So you take those ones into account. So let's work on a simple lighting circuit before we move on to the others. So this is an example of a lighting circuit we are just going to do. I think most of the stuff you did in first year, we shall not be going into so much of the details. So it's an example. Draw the schematic and wiring diagram of a staircase lamp system of 2 lamps controlled from 2 positions. Now we know if the case is to be controlled from 2 positions, to click into a mind, we need the 2-way switches, and 2 of them. There are always 2 of them. In this case, S1, you can switch the lights when you're going up the stairs. When you reach the top, you can switch it off, and vice versa. So a schematic diagram will look something like this. I think the symbols I'd given you the first time when we met to work out the symbols. I'll be giving them to you as we go along the way. So single pole, 2-way switch, single pole, 2-way switch, and the 2 lamps. And this one is our intake position from where the power is coming from, the kind of symbols we use. Now in your examination, in case there's a question, it will be in wording like that, is for you to come up with the drawings. So that will serve as the schematic diagram using the schematic symbols. Usually single line is not drawn to any scale. As you draw it, the symbols will tell us what the components are. Then the straight lines, we know our conductors which run to connect to the various accessories. Then when it comes to the wiring, you know the live, we go through a fuse, then come to the S1, is a 2-way switch, then go to the other switch, and then on to the lamps. And similarly, the IE tells us we need to also have the ECC, the earthing continuity conductor, to run, to be available at all those various points. The reasoning being, in future, we may need to connect a circuit here. In our case, it may be a fluorescent lamp which needs the earthing. So the wiring diagram would look something like that. At the moment, the cable size we use, the one that's being used currently in the market, is the 1.5. I hope with the IE revised regulations, we might change over to the 1. And then from the live, the cable that is carrying the power up to the accessory is usually color-coded red. Here, we have these 2 here. These are referred to as straps. And they'll also be red. And in this case, this will be the color of our insulation. Similarly, the lighting field here, this one will be red. And this one here connecting the live here to this other one here, that one will also be red in color. Now after passing through, in this case the bulb, the voltage will drop down to 0. It will be consumed here to produce the lighting. So as it comes out, this one here will be black, and this one here black, all the way to the neutral. So in this case here, R is for red. Then we have a B for the black. Then we shall also have the neutral, which is a combination of yellow, green. Green with yellow stripes, or vice versa. So this one here is the one which will be green. Green stroke yellow for the earthing. So to be something like that, we are putting the color coding. Now a situation may arise whereby for this installation, maybe all the cables you are having are colored red. So in case you want to run the neutral, in the red, you normally say you put a label, usually where you are terminating it. If you want to use it as a neutral and the cable is lead, you put in a label here to indicate the color it should be. In case this is a neutral and this one is red here, so here you put in the insulation, which is not the insulation, the insulating tape, which is black. Indicating it should be black. Likewise, in case you have got black, you want to use it to live, you use the insulating tape here, black, or you can also have some sleeves, the color of the cable that you want, and of course our termination will be coming out something like that. So in case the cables are not there, you can use insulating tapes or sleeving to indicate whether it should be live or neutral. But the practice is, for the live we use red, for the neutral we use black. Now this will apply if you are we are installing in conduits. If you are doing surface wiring, the cable will be sheathed. So in case you have a sheath, then you have to expose the insulation before you get to the conductor. So here, this one we have a sheath and the insulation, and here we have the conductor. This should be about 2.5 millimeters, an inch, about 2.5 mm. And this is where, in case it is red, usually the insulation is the one which is coded. Much of the sheath is gray or black. So in case the cable is sheathed, surface wiring, then you need to have about 2.5 mm to expose the insulation, which is the one which is coded, and then your conductor. And in case you are using the wrong cable, this is where you put in your tag to indicate the coding. So that is a small example. The other one, we can do a final design for us to finish the circuits on our lights. So we have a look at example 2, which is design a staircase lighting system such that as you go up or down the stairs, on operating the switch, the light ahead comes on and the light behind switches off. Assume 4 switches which are on the landings and 4 lights. Now, I've drawn the schematic diagram for you. I think it should be something like that. Now, when you get that one, you come up with a schematic diagram. Now, you may read that one there, and you come up with a different schematic diagram. That is the one I thought about. I can utilize these kind of switches to come up with a circuit. Think about it. Maybe you can use other type of switches, but to fulfill that arrangement. So, if you follow my schematic diagram, then do the wiring as an assignment, and then we'll continue from there next time. Remember, sometimes the designs you are told by people to do, they may be workable, there may be no solution. So unless you try, you cannot, you'll not be able to tell whether it can work or not. If it doesn't work, do modifications, go back again to the drawing board, and then we'll continue from there next time.